Dear students, in last classes we have studied the derivations for inductance of a single phase line, three-phase line with conductors placed symmetrically and unsymmetrically. Today we will take up the new topic, that is to derive expressions for the capacitance of single phase line and three phase line with the conductors placed symmetrically and unsymmetrically. So to do that, first we must have the idea of electric field intensity due to a conductor having charge on it. Electric field intensity due to infinite line charge. Let us consider a long wire having the charge q coulomb per meter. Due to this charge, there will be the electric flux around this conductor in all the directions. Due to that flux, we can calculate electric field intensity E at point P, which is R meter from the conductor. Let us say we consider point P here. Now intensity at this point will be due to the flux in the direction normal to the line conductor. The distance between point P and the conductor is R meters here.
Now we can calculate the electric field intensity at point P using Gauss law.
Before we do that, let us write few lines about this arrangement here. Students, I forgot to press the record button here while writing this note. So please copy down this. Just I will go on reading it for you. Consider a long wire having the charge q. That long wire having charge q is here. Coulomb per meter. That means this charge q is per unit length of this conductor. If conductor is of 1 meter length, then on it there is q coulomb of charge. If conductor is of 2 meter length, then there will be 2 coulomb of charge on it, and so on. as shown in figure above. Using Gauss law, the field intensity E at point P, that means we are going to calculate field intensity at point P, which is denoted by capital E, and this point P is at R meter from the conductor. That is, this point P is R meter from this conductor. How to write the Gauss law then? The Gauss law is written here as D into ds of closed surface integration equal to capital Q, where D is electric flux density. Like magnetic flux density, here we are considering what? Electric flux density. ds is differential area, very small incremental area we are considering, with the direction normal to the surface. And capital Q is total charge. Enclosed by the surface area ds. How much charge is enclosed by this area ds, small area ds, that we are calling as capital Q. Here we have written with the direction normal to the surface. With the direction normal to the surface means that the flux density D that we are going to consider here is normal to the surface ds at point P. The flux density at point P considering the cylindrical shell of radius r and length L will be calculated using Gauss law. So let us consider here conductor of certain length with q coulomb of charge on it per meter length. Around this, if we consider a cylindrical strip, this small cylindrical strip will be enclosing certain amount of charge. That enclosed amount of charge is nothing but Q into L, where L is the length of cylinder. It's very small now. And using the charge enclosed and the curved surface area of this small cylindrical strip, in Gauss law we can write, before that, right here, the enclosed area will be 2 pi RL and total charge enclosed will be Q into L. Thus, in Gauss law, D into the small surface area is nothing but curved surface area of this cylindrical strip. If radius of this cylinder is R, curved surface area of this strip is given by 2 pi R into L is equal to Q into L. On both sides we are having L, they will cancel each other. Therefore, now we can write capital D equal to Q upon 2 pi R. The electric flux density unit is Coulomb per meter square. The flux density and the field intensity are related by D equal to epsilon E. If medium is air, then epsilon will be equal to epsilon naught therefore electric field intensity E becomes Q upon epsilon naught into 2 pi r volts per meter. Now let us call this as equation 1. Next we will take up potential difference between two points due to line charge. I hope you all know the difference. I hope you all know the definition of potential at any point. The potential at any point is defined as the work done in moving unit positive charge from infinity to that point. What is potential? Potential at any point is defined the work done in moving unit positive charge from infinity to that point. If 2 points P1 and P2 are at distances R1 and R2 from the charge, field intensity E along any path joining 2 points as V is equal to minus integration from limit R2 to R1 E into dr. We have seen that E has unit of volts per meter. That means E gives us work done per meter. E gives us work done per meter. We are taking minus sign here because the limits of integrations are reversed. R2 is greater than R1, but here we are taking limits of integration from R2 to R1. That is why we are considering here negative sign. That is equal to minus integration from R2 to R1, substituting the value of E, that is Q by 2 pi epsilon naught R into dr. E value we are substituting from equation 1. That is equal to Q by 2 pi epsilon naught integration from R2 to R1 with negative sign (1 by R dr). On simplification we get plus Q upon 2 pi epsilon naught ln of R1 by R2 volts. Let us call this as equation 2. Negative sign used as unit charge is moved against the field. Next we will take up capacitance of single phase line. A capacitor is an energy storage device. It consists of two parallel plates. Between the two parallel plates, dielectric medium is placed. The two parallel plates are used as the terminals of capacitor. The capacitance of a capacitor is defined as the ratio of charge on capacitor to the potential difference between the conductor. Capacitor is an electric device which consists of two conductors also called as plates separated by a dielectric medium and used for storing electrostatic energy. Capacitance is defined as the ratio of charge on one conductor or plate to the potential difference between the conductors. To derive the capacitance formula, for single phase line following assumptions are made. First one, charge is uniformly distributed over the surface of conductor so that the flux is radial Second one, effect of earth is neglected. Let us consider the two conductors shown in figure below. Here the two conductors A and B are separated by distance D. If the radius of conductor A is R and if conductor A is having a charge density of Q coulomb per meter, then at point P, which is situated at distance x from the center of conductor A, the electric field intensity may be written using equation 1. If the charge density at conductor A is Q coulomb per meter and radius of each conductor is R, the electric field intensity at P x meter away from conductor A may be written as E is equal to Q upon 2 pi epsilon naught x using equation 1. However, the electric field intensity at point P from the center of conductor B having charge density minus Q coulomb per meter will be, here we are taking minus Q because if conductor A is go conductor, then conductor B will be return conductor for single phase system, and hence the charge flow direction in two conductors will be opposite. If I take the direction of charge flow in first conductor as positive, then the direction of charge flow in conductor B I have to take as negative. E will be equal to Q upon 2 pi epsilon naught D minus X, because the total distance between two conductors is D meters. Point P is at X meters away from conductor A, hence point P will be at D minus X meters away from conductor B. Since both the fields are in the same direction, the total electric field intensity at point P will be Ex equal to Q upon 2 pi epsilon naught x plus Q q upon 2 pi epsilon naught q minus x. The potential difference between the conductors will be VAB equal to minus integration of Ex dx between the limits d minus r to r. That is equal to, by substituting for Ex from say equation here 3, we get q upon 2 pi epsilon naught inside the bracket ln of x minus ln of d minus x. To substitute for limits from d minus r to r. That is equal to q upon 2 pi epsilon naught into the bracket ln of d minus r minus ln of r minus ln of r plus ln of d minus r. Q by 2 pi epsilon naught into the bracket ln of d minus r into 2 minus 2 times ln of r. If we take 2 common outside, 2 and 2 will cancel. Finally, we will have q upon pi epsilon naught into the bracket ln of d minus r by r volts. In case of single phase transmission system, the distance between two conductors, that is d, will be much greater than r. If we neglect r when we calculate the difference here, that is d minus r, then this equation will turn to q by 2 pi epsilon naught into the bracket ln of d by r. If d is much greater than r, then d minus r will be nearly equal to d. Therefore, VAB will be equal to q upon pi epsilon naught into the bracket ln of d by r volts. and capacitance between two conductors will be CAB equal to charge on one conductor divided by voltage or potential difference between two conductors, that is Q by V, equal to pi epsilon naught divided by ln of d by r. Farad per meter. Let us call this as equation 4 and this as equation 5 now. The capacitance between two conductors is given by CAB. Sometimes it is also required to calculate the capacitance of the conductor with respect to neutral. If the capacitance between the two conductors is represented as CAB in this way, the same system can be shown with a neutral point as in figure 2 here. Here N is neutral point. CAN is capacitance between conductor A and neutral, and CBN is capacitance between conductor B and neutral. CAN equal to CBN equal to 2 times CAB, because here two capacitors of equal value are connected in series, and we know that when two capacitors are connected in series, the reciprocal of equivalent capacitance is given by the sum of reciprocals of two capacitors. If these two are equal, then one upon CAB is equal to times any one of these two, or any one capacitor value, that is between neutral and conductor, is given by cross multiplying 2 times the capacitance between the two conductors. Dear students, I will stop the class here and continue in next class with capacitance of unsymmetrically spaced 3-phase lines. Using that, we will also calculate the capacitance of symmetrically spaced 3-phase lines. Thank you.